The standard Common AI can already produce much more competitive results than other existing tools. Advanced Common AI may allow XGen to achieve even better results. To use it, the user needs to adjust the content of the XGen configuration file associated with the AI model, and then follow the same interface procedure to train. XGen can be used to search for model architectures, such as prone ratios or the width or the depth of the deep neural networks. But users can also specify the model architectures themselves if the search is not needed. For example, a user can have a pre-trained dense model and one can specify the prune rate to be 75%. XGen can then prune the model to 75% sparsity by modifying the model configuration files. Let's look at an example for ResNet and see how we can configure XGen to do so. First, let's look at the configuration file of xgen.json of the ResNet. The configuration file of different neural networks are similar. It consists of several general training attributes, such as the GPU to use, the random seed, or the pre-trained model path if it exists. Then there are several training hyperparameters, such as the number of epochs, the learning rate, the batch size, and the optimizer, and so on. After that is the prune session, where users can specify the pruning configurations. For default configurations, the prune method is null, so XGen will do the search. We can first change null to magnitude to do magnitude-based pruning. Then we can specify the prune rate to be 75%. This is all we need to do to modify the configuration file to let XGen prune the ResNet model to 75%. We then save the model and run the XGen. We choose the ResNet model. We use ImageNet. We choose customized operation. Let's use just one GPU as an example. We select the batch size, the learning rate, the number of epochs, and the absolute path of the pre-trained model that we have seen. The training starts. As you can see, the model is loaded. The dense model is loaded. And you can see that the model is loaded and all the convolutional layers are pruned to 75%. The pruned model will be fine-tuned for some epochs based on the input from the user. Let's look at another example to select a subset of layers to prune. First, we join this folder. We need to create a file called prune.yaml. The YAML file consists of several key value pairs. The file starts with the string pro_ratio. The key is the pruned layer's names, and the value is the pruned ratio. Assume we only want to prune 2 convolutional layers in the first block, and the prune ratio is 60% and 80% respectively. We write the file as this, and we save this file. In order for XGen to prune the 2 layers only, what we need to do is to change the prune method to magnitude as in the previous example. And we need to add the file name to prone layers. We can save this xgen.json and run the xgen. We follow the procedure as before. We choose the ResNet architecture. We choose the customized operation. Assume we use one GPU to show this example. Choose the batch size, the learning rate, the number of epochs, and we input the pre-trained model path. And the training starts. As before, the model is loaded. Okay, we can see that only these two layers are proned, and their prone ratio is 60% and 80% respectively. The training will continue until the specified number of epochs are completed. Look at this example of customized and fixed scaling factor for EfficientNet. In order to show the model architecture has changed based on users' input, we can add one line in the training script to print out the model architecture. Let's look at the training script. The training script is this training script main. So before, we can see there's no print model. After we inserted this print model, we can print the model architecture, and we can see the difference by using different scaling factors. We save this training script. Then we open the configuration file for the EfficientNet. Since we do scaling, we do not need the pre-trained model. So we can change the pre-trained model path to null. And delete the rest. Then we can scroll down to the scaling section. Then we look for the variable name for the scaling factor in the scaling section. We can see it is the width multiplier. So we look for the width multiplier within this xgen.json, and we see this width multiplier here, and now the value is 1.0. Let's save this configuration file and run xgen to look at what the model architecture will look like. As before, we choose the EfficientNet for ImageNet. We choose the customized operation. Let's use the first GPU to demo. Choose GPU size. And we do not need the pre-trained model. And the training starts. It didn't involve the loading of the pre-trained model now. Because we print out the model architecture, we will see that it will print out the model architecture for all the EfficientNet layers. Just take an example. For example, the last conv head has input 32, output 1280. This is input and output size for the EfficientNet. we terminate this training and we try to modify the xgen.json for the configuration files. We look for the width multiplier here. Previously it's 1.0 and the value that we see is like 320 and output 1280. Now we change to 0.7. So all the layers will be scaling down by like 30%. We save the configuration file and we run xgen. Again, we use EfficientNet for ImageNet dataset. We choose customized operation. We use the first GPU. Choose the batch size, learning rate, and number of epochs. We do not need the pre-trained model. And the training starts. So remember previously, these two numbers are 320 and 1280. Now everything is multiplied by 0.7. That means our scaling factor is effective. So to change and fix the scaling factor, we'll first identify the variable that xgen is controlling by looking at the scaling session in the xgen configuration file. Then we find this variable in the xgen.json and change it to the value the user wants. Last, we change the pre-trained model path to null to avoid loading the wrong model. After all of these, we can follow the same procedure to train the model with the desired scaling factor or the desired model size.